Hey everyone, Mr. Hauk here. In today's video, we're going to start looking at limits algebraically. Alright, let's go ahead and get started. So, we spent the last couple of class periods looking at limits from tables and looking at limits graphically. So today we're going to start really looking at algebraic approaches to evaluating limits. We're going to start with today's lesson pretty basic, and we're going to start by looking at a few properties of limits. Okay, so starting here, let's look at our first one. Let's let b and c be real numbers, and let's let n be a positive integer. So then, we want to go ahead and try to understand, well, what would the limit as x approaches c of b be equal to? Well, if we think about this for a second, if the function that we're using is just b, that's a constant function. So think of that as a function of x is equal to b. Well, a constant function is just going to be a horizontal line. Going through whatever b is on, in this case, the y-axis. So if we're trying to evaluate a limit as x approaches some number c for a constant function, well, it's not going to really matter where c is. As we approach c from the left and the right, because it's a constant function and we have a horizontal line, the limit is just going to be whatever the constant is. So the limit of b as x approaches c is always going to be b, or in other words, the limit of a constant function is the constant itself, regardless of what x is approaching. Okay, again, it's because these constant functions are just horizontal lines, so it's not going to matter what x is approaching, the limit's just going to be b. All right, for this next one, we actually need to make a quick little change. We actually want this to say the limit as x approaches c of x. So make that change in your notes. Make that an x right there, okay? But basically this is saying, okay, well now imagine that you're taking the limit and your function is, y equals x, or f of x equals x. And it's the linear function that we've seen quite a bit. You used it quite a lot in Algebra 1 and 2. And so here I've done a quick little sketch of y equals x, or f of x equals x. And it's just a linear function of slope equal to 1 that passes through the origin. Well, if we're going to try to find the limit of y equals x as x approaches c, well, the thing about this function is that whatever x does, y does as well. So, because, it's just a linear function of slope equal to 1. So as we approach c on the x-axis, well, because y is mimicking whatever x is mimicking, the y values will also be approaching c. So in this case, the limit of x as x approaches c is going to be c. Okay, and then our third one, let's say we now have a power function x raised to some positive integer power n. Well, it turns out that the limit as x approaches c for power functions with positive integer powers of n can be evaluated by substituting c in for x. So really, and this is the power function right here. Let's say it was like f of x equals x squared. This is a power function where the integer power is 2. If we had something like that, if we wanted to calculate the limit as x approaches 2 of, say, x squared, then that's just going to be 2 squared. We take whatever this is, we plug it in for x. Okay, and you'll see some examples of these. So here in our first example, we want to calculate the limit as x approaches 2 of 5. Well, this is a constant. 5 is a constant. So if we graphed it, f of x equals 5, we'd have this horizontal line going through 5 on the y-axis. And let's say, we're having x approach 2. Well, here's 2. But it's not really going to matter if 2 is right here, because as we approach 2 on the left and on the right, because it's a constant function, a horizontal line, the limit's just going to be that constant number 5. Okay, approach it from the left or right, no matter where that x value is, those values are converging to the same location. All right, here in our second example, let's find the limit as x approaches 7 of x. Well, we have, the line f of x equals x, or y equals x, and if x is going to approach 7, let's see, 1, 2, 3, 4, 5, 6, 7, so we're approaching right here, well, the y values are just going to mimic that. So the y values will also be approaching 7 in this case. So really what we're doing here Notice this is really a power function with an exponent of 1, which still meets this criteria. Remember, to meet this criteria and just be able to plug c in for x, you just have to have a power function with a positive integer exponent. Well, 1 is technically a positive integer exponent, so we're really just taking the 7 what the x is approaching, and we're plugging it in for the x right there. Okay. And then here, example 3. Let's find the limit of x squared as x approaches 9. Again, this is just a power function where the integer exponent is positive 2. Well, let's just take the 9 and let's plug it in for x. So we get 9 squared instead of x squared, and we know that 9 squared is 81. So really what this is going to show us is that in these examples right here, and you'll see this on the back of the notes, if you can take the number that your x is approaching, you can plug it in, and if it works, that's going to be the limit, which is actually pretty cool. So let's do some more examples like that on the back. So theorem, if you can evaluate the limit by substituting the value of c into the function, then do so. This will end up being the limit. So check out example 4 here. We're going to show this using a number of different methods. So example 4 has us calculating the limit of 2x plus 4 as x approaches 3. Well, let's try this little piece of advice right here. Let's try to just evaluate the limit by substituting the value of c into the function. So c is the number that x is approaching. So let's just take 3, what x is approaching, and let's just plug it into the function for the variable x. If we do that, we'd have 2 times 3 plus 4, which is going to be 10, because 2 times 3 is 6, 6 plus 4 is 10. So the limit as x approaches 3 of 2x plus 4 equals 10. Now let's say, Mr. Houck, I don't really believe you there. Can you show me that on a table and on a graph? Well, sure, let's do that. So let's look at it on a table. For a table, we know that we want to make sure that the left-sided limit, and the right-sided limit, as we approach 3, they need to match each other. Well, if we just plug all these values into the function, 2x plus 4, or if we use something like a TI-84 calculator or Desmos to make the table for us, this is what we would end up getting. So we have this table with these y values right here. And notice that as we approach 3 from the left, the y values are converging to 10. And as we approach 3 from the right, the y values are also converging to 10. So from the table, the left-sided limit right here is equal to 10, and the right-sided limit right here is equal to 10. And we know that if the left-sided limit and the right-sided limit are equal to each other, then that's what the limit is equal to. So the limit as x approaches 3 of f of x is equal to 10. So that's showing the same result from a table that we just showed by plugging in the c value into the variable. And let's do one more quick method. Let's say, okay, well now let's look at it on a graph. Well, here's our graph. This is the graph of y equals 2x plus 4, this function right here. And notice that as x approaches 3, so our x values are going by 1s, 1, 2, 3, 4, 5. I have the y values going by 2s here in this case, 2, 4, 6, 8, 10. Well, notice that as x approaches 3, the y values are approaching 10 right here. Okay. So, but the big thing here that I really have to stress, and it's the part that I highlighted up here, it says if you can evaluate the limit by substituting the value c into the function. It's not always going to be possible. You're not always going to be able to plug in what x is approaching into the function and get a clean answer. And you'll see an example of that here in just a minute. But for now, let's try a couple example problems. So, example 5. We're not going to worry about trying to prove it graphically or prove it with a table. Let's plug in what x is approaching into the function and see if we get a clean number. So if I plug in 4, we get 2 times 4 squared plus 3. Using order of operations, we'll do the 4 squared first, which is 16. Then 2 times 16 is 32. 32 plus 3 is going to give us 35. So the limit as x approaches 4 of 2x squared plus 3 is equal to 35. Again, we had this function, and we just plugged in what x was approaching into the function, and we got our limit, okay? What about example 6? Let's evaluate the limit as x approaches 4 of x over x plus 1. Well, again, let's take x approaching 4. Let's plug it in for both of the x values. So 4 over 4 plus 1, which will give us 4/5. That's what our limit is approaching. So you might say, well, what do you mean by if you can evaluate the limit? Because it looks like substituting the number in for x has been working every time. Well, here comes example 7. So example 7 says, evaluate the limit as x approaches 0 of the sine of 1 over x. And if we try to plug in 0 for x, we get sine of 1 over 0. And the problem is, we know that 1 over 0 is an undefined term. You cannot divide by 0. So the question is, where do you go from here? Well, I think, in my opinion, one of the easier things to do is, once you have this undefined term, is to try a different method. And for this example, I went ahead and tried graphing next. So let's go ahead and graph the sine of 1 over x. Nice, let's pull up a little Desmos graph. And let's type in functions sine 1 divided by x. And what we get, if you look at the graph here, as we are approaching 0 on the x-axis, the y values keep bouncing up and down and up and down. And the closer we get to 0, the more the y values bounce up and down. We call this oscillating behavior. And we saw this on the most previous set of notes where we talked about the 3 ways that limits don't exist. And one way that a limit does not exist is if you experience oscillating behavior as x approaches whatever number it's oscillating around. So we can see that on the graph, we will see oscillating behavior as x is approaching 0. Therefore, the limit of, as x approaches 0 of the sine of 1 over x does not exist. Okay, so that's what we mean by, if you can evaluate the limit by plugging it in, by substituting the value of c into the function, then do so. It'll work for several examples, but when you get these undefined terms, these terms where something is being divided by 0, then simply substituting the value of c into the function is not going to work.